And the next contributed talk is called DeepCopy, Grounded Response Generation with Hierarchical Pointer Networks. And the talk is going to be given by Abhinav Rastogi from Google.
Yeah. Thank you. Hi, I'm Abhinav. Today I'm going to talk about our work on response generation. So we need grounding in response generation because we want to make conversations more natural and engaging. For example, suppose we have a restaurant recommendation system which recommends restaurants to users. And we also have reviews for those restaurants available on Yelp. If we can include information from these reviews in the response of the system, then we can make the system more engaging. So this is the motivation for grounding our responses in knowledge. So this area has been quite gaining like a lot of interest in research recently, and we have realized that sequence-to-sequence models which convert dialog context directly to response are not like good for for modeling this problem, because these models end up encoding the knowledge in the model parameters, and also we need a lot of data to cover all the knowledge if we want to just use this approach. Also, as new knowledge becomes available, such as new reviews come up, it's difficult to incorporate them in the model, and we need to retrain the model. So the idea is to use external knowledge as an input to the system so that we can generalize to new knowledge that comes in. So our contributions are, we propose a few models for response generation which incorporate external knowledge. We provide comparison with several baselines, and we propose a multi-seek-to-seek model which does hierarchical attention over the knowledge facts. And also we extend the pointer generator networks to copy content from the external knowledge. So let's look at the data sets which are available for this task. So first one is DSTC7. So this consists of conversations obtained through Reddit threads, and the entire Wikipedia article associated with the conversation is the external knowledge. We also have Wizard of Wikipedia, which is a fairly new data set, and they have a poster today. And on the other hand, we have Convey-I2 data, which consists of natural conversations between two humans guided by their personality description. Each of these humans are given up to 5 statements describing their personality. And the key feature here is we don't need a retrieval step over all the facts because the set of facts is very small. So this helps us isolate the effect of retrieval step and focus more on the response generation task. So we use this Convey-I2 data set in our work. So this is what Convey-I2 data set looks like. We have 2 personas given to the participants, and they engage in a dialogue. So we generate 1 training example for every utterance. So our training example consists of a response. All the preceding utterances of the response are taken to be dialog context, and the persona corresponding to the response is taken to be the set of facts. So our task is to use the facts and dialog context as input and generate the response. So a few challenging things about this data set is the usage of facts. So we need to copy information from the persona sometimes. Hence, we believe copying information could be useful. There are some hallucinated facts, where people make up facts while doing these dialogues. And this is challenging because difficult for the model to just hallucinate facts on its own. And there is also humor, which I don't know how good the model will be at. So yeah, these are the challenges of this data set. We use the traditional automated metrics. And as promised in our future work, we also did human evaluation. So I'm going to talk about that today. So one metric we use is fact inclusion, so how many responses include a fact. Then we have factual correctness, like how many responses include a correct fact. So fact inclusion is an upper bound on factual correctness. We have coherence, and we have naturalness. So I'll quickly skip over, I'll quickly go through the baseline models in interest of time. So first we have seek-to-seek with attention. So we use a context encoder which encodes the dialog context and gives us a final encoding of the, an encoded representation of the context as shown in red. And we have intermediate token representations for the context encoder. At each decoder step, we attend over these intermediate representations, and the decoder state along with the attention vector is used to generate a distribution over a fixed vocabulary. So this happens at every decoder step, and we generate word by word. So a simple extension for incorporating fact is to just concatenate it with the dialog context. So we do that in this work. We concatenate a single most relevant fact. We do it in two ways. So first one is best fact context. So we use the TF-IDF similarity between the dialog context and all the facts to obtain the best fact, and that is concatenated with the context. Second is best fact response, which is like a cheating baseline where we use the ground truth response to get the best fact. So this is kind of like an upper bound for such models. This is what the results look like. One important feature we see is incorporating a single fact. It helps us in perplexity, but it loses naturalness. So this may be due to the simplicity of the model in which, like in the way we incorporate facts. And we also, another thing to notice in the ground truth is like low factual correctness. So this is because people start hallucinating facts. So we kind of take care of that in the evaluation metrics. Like if there is a hallucinated fact, then we mark it as wrong. So we see that a lot of that is present in the ground truth. Next, we have memory networks, which help us obtain the encoded representation of all facts. So we encode all the facts using a fact encoder, which gives us a final fact encoding. These encodings are converted into two vectors by two different transformations. Then we use the context vector to attend over the green vectors to give us attention weights. And then these weights are shifted over to the value vectors shown in blue, and we get a linear attention weighted combination of these blue vectors, and these are added to the context encoding and fed as initial state to the decoder. And then we use the, like at each decoder step, we simply generate the distribution over vocab. So the only change here is how we initialize the decoder state. So this is the module for like memory network, which can be summed like this. Then we add to this attention over context and also attention over facts. This is another, so here we only attend over the fact encoding at every step, and we also do both of them. So like basically concatenate the two attention vectors. So this gives us four variants of the memory network one. And here we observe that if we only attend over facts, it gives us bad fact incorporation as seen in the fact metrics for the fact attention model. And if we do like attend over both, then we get the best on like human evaluation metrics out of all the variants. Now moving on to pointer generator networks, it's a extension of the sequence to sequence with attention model, where we use the attention weights over the context token to induce a distribution over the tokens in the context. So we now have two distributions, and they can then be combined in a software to give an overall distribution. So one key fact here is we are getting a distribution over fact tokens, which may contain out of vocabulary tokens. So in effect, we are able to even generate out of vocabulary tokens, which are present in the context if we do this. So the motivation for copying was like it helps in reproduction of information present in the context, and also it enables the response to contain OV entities during inference. So we have three variants for the copy model, which are corresponding to the three variants of the seek-to-seek model, which we see. The third one is like a cheating oracle method, where we use the best fact obtained from the response. So here are the results, and we see that copy mechanism performs like on human evaluation. Copy mechanism gives the like improves the corresponding seek-to-seek model for all the models. And we also see a good drop in perplexity for the best fact model here. So moving on to our first contributed model, this is multi-seek-to-seek. So we saw in sequence-to-sequence models, we condition the response on a single fact. In memory networks, we were able to condition it on all the facts, but we were only attending over like the encoded representation of every fact. So now the question we asked is like, can we attend on every token of the fact? Like not just at the encoded representation of the complete fact, but like at token level. And then we also saw in copy mechanism, we could copy tokens from the context. So the question we asked is, can we copy tokens from the facts as well? So, to provide answers to these two questions, we formulated two models. So the first one is multi-seek-to-seek. So we start with like a context encoder and like a decoder. We also have fact encodings. So these are like the intermediate token representations for each fact. At a decoder step, we use the decoder state to attend over these tokens. So this gives us, like in this example, it gives us 3 distributions over all of the fact tokens. Then we do the attention-weighted combination of these intermediate representations to get the 3 fact vectors. And then we do another attention over these fact representations to give us like a distribution over fact level, over facts. And we also use the decoder state to do attention over context. And by summarizing all the 2 representations, we get 2 vectors, one representing the entire context and one representing the entire facts. These are then used together with the decoder state to generate a distribution over the generation vocabulary. So here we can attend to different fact tokens at each decoder step. And this is like a hierarchical attention. DeepCopy is a simple modification of this. So we saw in seek-to-seek, like in the pointer generator networks, we used the attention weights over a context encoder to generate a distribution over the context tokens. So here we have attention weights over the fact tokens. We just use it to induce a distribution over all the fact tokens. So in effect, we had like a overview of DeepCopy. We had a dialog context, which was fed to a decoder, and we had a knowledge source. And at each decoder step, we do attention over context and knowledge source. Based on the attention vectors, we generate a distribution over the fixed generation vocabulary. Using the attention weights, we induce 2 distributions, one over context tokens and one over knowledge tokens. And then we softly combine these 3 distributions. By the way, these combination weights are like dependent on the time step. So at every time step, we combine them, like we can give different weights to all of them. So then, in effect, we can copy tokens from the facts as well. So as compared to like other models, we see that DeepCopy achieves the best perplexity score. So here I have removed all the models which were using the cheating models, basically, which were using the response. So here we see DeepCopy gives us the best perplexity. And it also improves upon multi-seek-to-seek over all evaluation metrics. So the only difference between multi-seek-to-seek and DeepCopy was the copy mechanism. So we see copy mechanism helps in like human eval as well as perplexity. And we also see that best fact context plus copy, it's a very strong baseline in terms of human evaluation. So like it was a very simple model, right? We just used the dialog context and retrieved the best fact and concatenated it with the context and had like a sequence-to-sequence model with attention. So in summary, we proposed a model, like few models for response generation, which use external knowledge as inputs. And we also proposed like strong baseline models for comparison. And we compared all these models using automatic evaluation metric as well as human evaluation. Yeah, that brings me to end of my talk. So happy to take any questions. Thank you.
Another extremely well-timed talk. Questions?
Hi, Stephen Roller from the Parlay team. we were really excited to see this paper. Very excited about the model. I think this is the model we were aspiring to on the Wizard of Wikipedia test. So I encourage you to apply it before we do. However, we did notice that the baseline models that you report have considerably higher complexities than the comparable baseline models in the original Persona Chat paper.
Yeah.
Do you have thoughts on this?
Yeah. So I think perplexity computation depends on the vocabulary size you use. So the results I'm reporting, they are on the dev set. So we used a fraction of the dev set for doing our tuning, since the test set is not publicly available. And to get numbers on the test set, we needed to submit the code, and we need some approvals, internal approvals for doing that. So these numbers are on the dev set. And we were not sure about the vocab size used. So hence we implemented all the baselines ourselves so that we can do a comparison.
I actually don't remember if vocabulary size was reported in the original Persona Chat paper, but it was not?
No, it was not. Yeah,
okay.
we checked that, yeah.
Thank you very much.
I'm curious if you know of some architecture or technique in order to generate those facts from conversation data.
Oh.
Because I'm assuming, like, if we're talking about a social bot or of some sort, we want to learn about the person. We want to kind of use those facts or use some NLG or just latent space as a sort of state about the person, and then be able to interact with them and build knowledge about the remote person.
Yeah, that's a very interesting extension of this problem. Like, especially we are interested in so I think what you mentioned is we have a lot of conversations between humans and between people, and can we use all of my conversations to know more about me? So I think one easy thing we can try here is just switch the role of facts and the conversation and try to generate that. But I am sure there will be much more elegant models which do this.
Thank you.
I'm curious about two things. One is the computation time, because you're doing a lot of attention and it's quadratic by nature. And then whether you take into account repeated facts when you're encoding everything.
Repeated facts as in?
So like repeating the same idea in the text, and whether you take that into account.
So that is in our future work, repeated facts. Yeah, look forward to our future work. And for, what was your first question?
The cost of computation.
Yeah, so that's again a good point. We saw that the attention models are little more slow. I don't have the numbers to compare them, but I think it was about 2x slower than just sequence to sequence. Yeah.
Okay, right, I think we'll stop there. Thanks very much.